Welcome, everyone. This is my pleasure to introduce George Porter, who's a research scientist in the computer science department at UCSD. George has a PhD from UC Berkeley, and he is going to tell us today about some of the really exciting work that his group has been doing in the area of data-intensive scalable computing.
Great, thank you so much. All right, well, good afternoon. By the way, thank you for your time and listening to this talk. It's my pleasure to come and talk about some of the work we're doing at UCSD on building balanced data-intensive scalable computing. And before I start, I just want to acknowledge the team of incredible graduate students that I have the opportunity to work with. Alex Rasmussen and Mike Conley deserve the bulk of the credit for this work. Joining them is Rishi Kapoor and Terry Lamb, who are two other students who have recently joined the project, and so they're kind of getting brought up on board. And Amin and I are sort of advising the project. And we have some project alumni, including Harsha, who you probably know from this department. So it's, certainly for this audience especially, it's, you know very well about some of the rise of these big data workloads that people are dealing with in industry and academia, in science, and in universities. These are workloads that have enormous I/O and storage requirements. So things like large-scale web and social graph mining. I had this really great discussion with some of the DB students about some of the problems that y'all are working on and some of the research you're doing. Collaborative filtering, things like finding books on Amazon that you like, et cetera. A lot of the large-scale data science that people are doing. It's even interesting that being a data scientist is like a job that you can do now. So that's actually something that you can say that you do. So people who take enormous unstructured data sets, figuring out problems related to those and extracting information. As well as high-resolution video. This so-called 4 and 8K video are very large-scale, sort of data-intensive motion picture formats that have a lot of storage, networking, and computing challenges associated with them. And what's great is that we live at this really awesome time where there's all this kind of flourishing of exciting research that's going on ways of solving these problems. And so both industry and academia have come up with all these really interesting research projects to address this. Things like Mapreduce from Google, its open source implementation as Hadoop, and various constellation of Hadoop-related research that's gone on just across the way a little bit at Microsoft with Dryad, et cetera. And it's actually not really that surprising that a lot of the companies that are dealing with these large data sets are also the kind of companies that have driven a lot of the research that has gone into systems that solve these particular problems. And so how do all of these systems work? They all work at a first approximation in a very similar way, which is instead of hacking on a single machine to solve the data problem, what we'd like to do is we'd like to hack on a whole bunch of machines. The idea is that we have these huge data centers that are full of servers, and we'd like to distribute a particular program across of these and sort of solve the problem by taking advantage of massive parallelism and scalability. And there's, of course, a lot of challenges that come out of operating at this particular scale. But one of those challenges is very much the fact that addressing these problems has really focused on scalability. And I want to really make this point and really emphasize this point that Facebook had to go from basically no users to 800 million users in about 7 years. Google had to go from no users to some undisclosed number of users, but presumably a lot, hundreds of millions, possibly a billion users in about 13 years. And so, we went from a situation where we had systems that didn't have any scalability at all, and yet we were able to grow in just a couple years hundreds of millions of new users. And so this is just kind of a miraculous result of these systems that got built. And so in a sense, now that we have the scalability and we've built out these systems, it's kind of interesting to think about taking a breath a little bit and looking at how we can actually get a lot of efficiency out of these. And the result of these is not just that we can now meet the needs of all of these users, it's actually that the side effect of these has been these enormous physical plants that host all of these computers. And so, companies like Microsoft have built these large data centers, $4.5 billion data centers alone. Even these results are a little bit out of date. The 64,000 square meter data center. Google has built a variety of data centers around the world. And Amazon has built this facility in Oregon, et cetera. And I know James Hamilton was here just a couple days ago, and I'm a big fan of his, and he talks extensively about a lot of the power and cost and other issues of building these data centers. And so the result of the scalability has been very expensive in terms of building out these things and running them. They have enormous energy demands, even dictating where they're located on the Earth in terms of lowering that energy demand, and of course environmental effects, et cetera. And so I guess, one of the things that's interesting is that now we've met these users, it's kind of, again, time to sort of take a break and look a little bit about what these things are doing. If we actually dive into one of these buildings that's hosting all of these servers, we see that in a lot of ways what we're doing is, in a sense, brute force scalability. So, there have been 10,000 node Mapreduce clusters deployed at Google and Yahoo and elsewhere. Well, maybe not 10,000 at Yahoo, but definitely at Google, that have incredibly impressive performance. And so, as an example, Yahoo has posted numbers for a large distributed sort they did of 100 terabytes of data. And they were able to harness about 3,500 nodes to sort 100 terabytes of data in less than 3 hours, which is an incredible result when you consider the fact that even keeping one computer running is difficult. And then if you have this many computers, the number of disks that are failing, network links that are failing, power supplies that are failing, et cetera, is extremely non-trivial. And so just getting that many machines to give you a result of any kind is kind of a miracle, much less in a short amount of time. But if you actually go in and look at what these nodes are doing, which we took their published results, and we just did a little bit of time in Excel to figure out that each node is basically contributing about 3 megabytes a second towards the aggregate performance of the system. And when you contrast that with the fact that even one commodity disk you buy at Fry's can support 100 megabytes a second, you realize there's a pretty large gulf between the delivered capacity of the system as a whole versus the underlying components that exist in individual nodes that make up these large-scale systems. And in case you think that maybe this is some isolated case based on the numbers from Yahoo, there's this really interesting paper that came from HP Labs by Anderson and Tusek called Efficiency Matters, where what they did was they took a lot of public results and they surveyed some different results of large-scale distributed systems that published some of their performance numbers, and they actually went in and made these computations. And what they found was that about a third of CPU capacity was left on the floor, and about 90+% of underlying storage capacity was basically thrown away in these systems. And so, so what we have basically is a system where we want to harness a lot of machines to solve large data problems, but it kind of drives you to ask, what if we went from 3 megabytes a second that we're seeing in practice to maybe 30 megabytes a second or 300 megabytes a second? If we could do that, what we'd be able to do is, either have 10x fewer machines to solve the same task, or we could solve 10x larger programs with the same equipment. And I think that this is really important for two reasons, which is that for large companies, in a lot of ways, it could prevent having to build new data centers. So if we can do more work with the same pre-existing footprint that we have, that saves a lot of money and we don't have to build new things. And so that's kind of useful for Google and Facebook type deployments. But I know that especially given a lot of the conversations I've had here at UW, it also helps the kind of long tail of people who aren't necessarily Google and Facebook, but they have big data problems as well. So this could be universities or colleges, nonprofits, government agencies, et cetera, that have limited budgets and want to solve a lot of large data problems and don't necessarily have the ability to address problems at the scale of places like Yahoo and Google. And so that's really driven the research that we've been doing at UCSD. And so the research question we've been looking at is, how do we build a highly efficient, data-intensive, scalable computing or disk system that improves per node efficiency by an order of magnitude or more compared to existing systems? And that's really the kind of thing that we've been looking at. And our approach to this has been to really focus on building balanced hardware and software platforms. And so I'm going to talk about a little bit in this talk sort of how we go about that and what we mean by that in the context of some of the applications I've described. And a key insight that we have taken towards looking at this is the fact that every time we touch a piece of data, so every time we issue an I/O, we'd like to also mutate that data in some way or another. And so we know that for certain workloads, we have a provably minimal number of I/O operations that we can perform. And so if we can manipulate the data every time we mutate that data, or every time we issue those I/Os, we can drive a lot of efficiency. And I think hopefully that will come out as I'm going on during the talk. If you have any questions, feel free to also ask me during the talk. I mentioned before the sorting thing. So in the talk, I'm also going to talk about sorting. So sorting is a case study, and it's an initial challenge application that we picked because we needed a workload for some of the other research we were doing. So this kind of became a side effect of what we were doing. The great thing about sort is that as a benchmark, it's very constrained and well-defined. We know what the input is, we know what the output is, and we know if we're correct or not, which is very important. And also, Jim Gray had created this annual sorting competition in the mid-'80s, which is he's very forward-looking, and it's kind of a way to compare systems across different vendors, different architectures, et cetera, in order to say how fast can we sort a particular amount of data. Now, when Jim Gray created the competition, the amount of data was quite small and can be sorted in less than a second on modern architectures, and so that challenge that he created has been scaled up over time and is currently at 100 terabytes of data. Sorting is also it's a very fun thing that involves systems research, networking research, computer architecture, and some database stuff. And so it's an interesting challenge probably. It's also, it's kind of surprising, but people actually do sorting in data centers. This is actually a problem that people have. And it's also kind of indirectly applicable because of the fact that I know from sort of personal conversations that places like Facebook, when they do a new rev of their code, they'll actually do a sort benchmark to see if they've regressed at all in terms of performance. And so it kind of approximates at a first order what real data center applications are like. So we kind of looked at it and we said, okay, this is an easy thing to do. Sorting is like what you teach undergrads. This is no problem. So we'll put a grad student on it, and like maybe in a week or so of coding, we'll have a system that's running. And we did this back of the envelope calculation based on the hardware that we have. And we figured out that we could beat the sort record with about 30 machines. And we had 52 machines, so we had some headroom, which was really great. So we figured, okay, we had a meeting on Wednesday, and we're like, okay, next Wednesday, come back with a sorting code, and then we'll do a day or two of tuning, and then we've got this benchmark, and it's going to be really great. And it turns out that was not the case. And I guess the key insight is that we thought that if we had a balanced hardware platform, it would be very easy to make use of it to build a balanced software and hardware system. And we were really wrong in that case. It's actually very difficult to build software that can efficiently bridge the network, the disks, the memory, and the compute. And so that's kind of the story that I'm going to be talking about. Just to give you a kind of preview of some of the goals, what we wanted to do is to be able to sort 10 to 100 times faster than the state of the art in terms of a per node rate. And we were also very interested in how that might play out in terms of energy efficiency. And so we also set out to kind of build the world's most energy efficient data sort, and I'll talk about that in a second. But just so that it's clear, we're not stopping with sorting. This was kind of our initial challenge application. The work that we've been doing since this work appeared at NSDI last year, and the work that we've been doing since then has really been generalizing it to support more general computation. And so we built a Mapreduce framework that currently works and runs on top of this, and we're interested in some other things as well. So if we look at generalizing before beyond sort, we started by building this Triton sort system that was a runtime piece of software that also did sorting. And after we were able to get this record, what we did was we kind of factored out the actual runtime that had to do with managing memory, managing CPU and buffers, et cetera. And we made sort kind of an application that sat on top of that. Since that paper came out, we built a Mapreduce framework as well that sits on top of it as well. So this is like another application. And then it's very easy once you've got that Mapreduce framework to put other applications as well. And so we have about half a dozen other applications that we built and that are running kind of at our cluster down at UCSD. And so the Triton sort system I'm going to be talking about is an application on top of this runtime architecture we're calling Themis. So that runtime itself we call Themis. And the thing to keep in mind is that Themis is a very simple thing. It's a data flow processing system that's distributed. And it looks like a lot of data flow systems you might be familiar with, where you have a directed acyclic graph of processing. Vertices do computing on data, and you have buffers that go along these edges and that go between the vertices. So this looks like very much like something like Dryad. In fact, we wanted to use Dryad, but we had trouble sort of getting access to the code and running it within our particular network, and so we ended up kind of writing our own system. And so it's a very fine system. The one thing that we care about in this is that we need fine-grained resource control. And so it's very important that we can, with very fine-grained control, manage buffers, CPU scheduling, memory, et cetera. And we can also easily vary them as well. And so that's really what we care about in terms of the system. The system itself, from a research point of view, is not that interesting. It's kind of more what we do with it that I think is a little bit more interesting. So we set out to build this balanced system. And what we mean by balance is, in terms of hardware, is we'd like to drive all resources to as close as 100% utilization as possible. Every system has some particular bottleneck, and we'd like all of the bottlenecks to be as close to each other as they can. So in other words, if we were to remove or lessen any one particular resource, the system should slow down. That's an indication of a balanced system. Modulo with the fact that we're limited by commodity choices. So we can buy a 10 gigabit network or a 1 gigabit network. We can't buy a 9.5 gigabit network, although there are ranges in between with InfiniBand and stuff like that. And balanced software is something that will fully exploit the hardware resources that we have. Of course, within the constraints of our application, not all programs necessarily admit parallelizable implementations. Now, it's funny, the thing that's kind of cool about building balanced systems, this is a very old problem. This is not something that we are having to deal with ourselves. And in undergrad classes, you'll talk about Amdahl and Amdahl balance. And Amdahl's law. And 40 years ago this year, there was this paper called The Design of a Metasystem. And this is a graph that I pulled out of that paper. And what's really great about it is that what the problem that was being addressed in this paper was the fact that they had this time-sharing system that they deployed out into the world. But then they found out that people started writing different programs than they were maybe anticipating. The usage patterns changed. And so something had to happen to make that system adapt to those changes. And so the idea is, you take measurements, you put them through this evaluation, you do some simulation, you give it to the system designer, and then you have modifications that go back in. And if you basically just replace the word time-sharing system with the Hadoop elephant, this might as well show up at SOSP last week in Portugal. And this is exactly what we're doing. So this is kind of like 40 years ago. If we fast forward to 20 years ago, Maslin and Pugh did this interesting work on fine-grained adaptive scheduling using feedback. So it's like software feedback systems for runtimes, distributed data flow systems, and actually even real-time audio creation. And there's this great quote, which was that, first we note that a smooth flow of data through the pipeline would best use the resources of the system, since each stage will be running at just the right speed without idling or congestion. And I mean, we could have put that in our paper from last year, and that's exactly the kind of spirit of the work we're trying to do. The major difference here, of course, is that as time kind of marches on, we have different points of technology along these different resources that change relative to each other. And so this kind of optimization problem is something that is always going to be happening and will never really necessarily solve. But we can learn a lot from previous work, so that's what's nice about working on the system. So in terms of an outline for the rest of the talk, I'm going to talk about some of the details of this try and sort challenge application, give some of the results of our manual tuning and balance that we did, and then I'm going to talk a little bit about how we generalize our system to other hardware configurations as well as other applications as well, and then briefly talk about some of the ongoing and future work that we're doing now, and then take questions. So we started by doing a co-design of our hardware and software. We got a grant from the National Science Foundation called a Major Research Infrastructure Grant, and so we had this money to build a new cluster, and we knew we wanted to do data-intensive processing, and it was like, okay, what are we going to buy with this? We didn't really know we were going to do sorting at this point, but the kind of problems we cared about were problems where you are I/O limited, and where you either don't have a working set at all, or your working set is so large that effectively, you cannot just stage data in memory, do processing, and then sort back out again. You've got to be able to stream data from storage through computing and then back out to storage over the network, possibly. And so what we did was we just kind of did a couple whiteboard type things, like say, well, if we have 10 gigabits a second, and we have 80 megabytes per second per disk, which is like a commodity SATA drive, that works out to about 16 disks or so. If we have 2 disks per core, which seems about right, that's about 8 cores or so. And then we figured we'd need about 1.5 gigabytes of memory per core. Later on, we realized that was about 3 gigabytes per core. So we did some of these kind of back of the envelope calculations, and we ended up building up this particular hardware platform. We had 52 nodes of some modern processors that basically had what I just described on the previous slide. So you have 16 disks, 10 gigabit NICs, and we have one switch in the middle. In terms of the architecture, there's this result by Agarwal and Vitter that says that if you do an external sort, you have to read and write the data twice in each case. So, so we know that we're going to have to read the data, write it, read it again, and write it. And what we tried to do was build a system that touched the data exactly twice in each direction. And so that was kind of one of the goals we set out. And so we decided we're going to have these two phases. We're going to have phase one where so if you want to think about it this way, imagine you have a cluster of nodes that all have local storage in them, and the data starts out randomly distributed among these nodes, possibly with skew, but it's across the nodes. The first phase of the processing is basically to read the data off the disks and get it to the right node. It's not going to be in order, but at least it's going to belong on the right node. And then in the second phase, we're going to read that data locally, sort it, and then store it back down again. So the network is used in phase one, network is not used in phase two. Phase two runs entirely in parallel. Phase one is a system where we have nodes talking to each other. So that looks something like this. We basically have, this is the point of view of each node. So we have a set of these 8 input disks, and we have 8 reader processes that are reading in parallel. So they read a buffer of data off the disk. They pass this to what's called a node distributor, which is basically just a hash distribution where we apply this hash function to the data, and we figure out what node it belongs to. And we copy this data into buffers that are destined for those particular nodes. Now, we're not doing any sorting in this part yet. We're just deciding what node it belongs to. And then when these buffers get full, we pass them off to a sender that's going to send them over the network to the destination node. So that's really quite simple. The read part here is all sequential I/O, so that can be done very fast. In terms of the destination on the other side of the network, what happens is data arrives destined for this particular node. And what we're trying to do at a high level in this phase is we've got a set of files that are spread out on these output disks for phase 1. And we want to make sure that all the data that belongs in a file, that all the data that belongs together goes in the same file, although it may not be sorted. And we want to minimize seeks whenever possible. So if we did a naive approach where as data arrived in, we just issued it to the disk with a disk write, what we would have is disks basically seeking all over the place. And that's not really what we wanted. And so we have this downstream part of phase 1 is all about staging data in memory so that we write data out with the minimal amount of seeks possible. So what happens is this receiver data, the data goes into a buffer, and we pass it to what's called an LD distributor. So we divide our physical disks into a number of logical disks. And each logical disk can be read into memory and sorted in memory. And so there's a restriction on how big these logical disks can be based on how much memory we have. And so we're going to hash the data a second time, and we're going to figure out which of these logical disks the data belongs to, and we're going to stick it in one of these partitions. And each of these partitions is going to be keeping data as it comes in, and I'll talk a little bit more about the data structure that's implemented there. And then we copy these to buffers, and then we have a very simple writer that will write these out. So at the end of phase 1, what's basically happening is the data has been partitioned not only across nodes, but also within a node across a number of different files such that they can be read into memory and sorted with an in-memory sort. So just to push in a little bit on what these stages do, and more importantly, how we actually did the manual tuning required to make the system work well, I'm going to kind of go through that pipeline again and talk about some of the computations we did to balance this. So in terms of the reader, where we're getting the data in off the initial disks, we know that a disk can go to about 100 megabytes a second, and we have about 8 of these disks. And so from the starting point, we know that we have to support, our pipeline has to be able to support 800 megabytes per second of sustained I/O. The reader process has very little computation. It's basically entirely I/O weight limited, and some memory operations. And so what we do is we have 8 reader workers, 1 per input disk, and they're all core scheduled on a single core. And that's very easy to do because of the fact that all they're doing is issuing an I/O and basically waiting around for it to complete. As you'll see, our systems have 8 cores, and most of what we're doing is I/O bound. And so it's not that we need the cores because we need a lot of computing power. What we really want to do is isolate processes from each other. So a lot of these stages, we want to impose some isolation. And so we took a very heavyweight but very simple approach of just putting these and scheduling these on different cores. The node distributor is going to run through this hash function, and it's going to append these tuples, 1 per buffer per destination node. And what this involves is a memory scan plus a hash per tuple. And we did some micro-benchmarking and found that there's about 300 megabytes per second per worker. And so we needed to instantiate 3 of these workers to keep up with our input rate. Now at this point, we've got to send this data over the network to where it belongs. Now we've got 800 megabytes per second coming into our sender stage, which is about 6.4 gigabits per second. And we're sending the data to about 50 other nodes. And so we need to sustain 6.4 gigabits per second across our nodes, but we also want to prevent pipeline stalls. And so what we really want to avoid is some disk on the downstream node ever running out of buffer space, because that represents some waste in our system. And so not only do we have to support 6.4 gigabits per second sending, but within each stream to a node, we also have to make sure that each underlying disk stream also gets about 100 megabytes a second. And so we have this requirement in our network layer for flow fairness and for a bounded interbuffer delay. So we can't send a bunch of data to one node and then wait too long, because then that buffer will run out. And so we have a certain amount of minimum good put per node. And we did a very, we started with a very simple implementation that just relied on normal kernel sockets. And what we found was that we didn't really have enough control over the thread scheduler. And so what ended up happening is we got a lot of unfairness. So even though we had enough buffer data to send, some flows would get the network a little bit longer than others. And so we ended up having disks that would basically stall out. And so what we ended up having to do is implement the thread scheduler at the application layer. And so we ended up implementing a single-threaded application that we were able to schedule very tightly. And so if you look at this kind of graph, this red line represents the minimum amount of data that we have to send in order to keep the pipeline stalls from happening. And the blue line that's kind of going underneath that was when we implemented a multi-threaded implementation where we had a thread per sender. And so we ended up pulling that code out and replacing it with a single-threaded implementation where we end up sending a bounded amount of data in a non-blocking way to each host, and we just have a very strict round-robin scheduler that we implemented at application layer. And that works out great because we're able to send data at 10 gigabits a second with a single thread and keep all of our downstream pipelines busy. But I do want to kind of point out that this does indicate that there's a little bit more research that needs to be done here because of the fact that because we had 50 nodes, it was possible to implement a round-robin scheduler that could support 10 gigabits a second. If we had 500 nodes, the amount of time it would take to visit each of these sockets and go back again and start over again would be long enough that we would end up with some pipeline stalls. And so in that case, what we'd need is a multi-threaded sender that was able to keep these busy. So that, I might revisit that a little bit later in the talk, but yeah, so the solution that we kind of picked for this works for our particular installation, but we're currently revisiting that, and we're going to go back and look at a more sophisticated way of actually sending data across our network links. So at this downstream side, we've got this thing called this logical disk distributor, and the thing that we're trying to deal with is the fact that if you think about skew in the underlying data set, although the data is generated randomly, the sorting benchmark requires that you support skew in the input data. And so it's very possible that you're going to get a stream of data destined for one disk, whereas you're not going to get necessarily data that's uniformly distributed across the disks. And so one of the major problems that we had to deal with was head-of-line blocking on the downstream part. And so we needed a data structure for managing these downstream buffers that wouldn't end up with this kind of head-of-line blocking problem. And so, and it also had to be able to support a very high write rate while supporting random seeks as well. And so the idea behind it, the kind of insight was that what we wanted to do actually is not to read data into very large buffers because once those buffers get full, we send them off to be written, and now if data comes in for that disk, we don't have anywhere to put it, and that's not good. So instead what we did is we decided we're going to create a ton of very tiny buffers. So we create like 1 million of these little 12 kilobyte buffers, and they live in a pool. And so what happens is as data comes in, we fill a little bit of buffers, we stick it on a linked list destined for that disk, and then we move on again. And so that way, as the writing stage is writing data down to the disk, it can start releasing in batches some of these little tiny buffers. And so that way we end up with this pool that doesn't really empty. And as long as there's some buffers in our pool, we can actually write data out. So it looks something like this. So imagine that we have at the top, this is like one of these buffers that came in for us, and it's got a bunch of tuples in it. And then this thing on the right, basically, we have one linked list per logical disk. And there's about anywhere from 1,500 to 3,000 logical disks on a single node. So you can think of this as a table of linked lists that maybe has 3,000 elements in it. So what happens is we're going to run through this buffer, and we're going to hash each tuple, and we're going to figure out what logical disk it belongs to. Like in this case, this one belongs to logical disk 1. So we're going to append that to this little 12.8 kilobyte buffer that lives over here. And then the second one comes along, and it belongs over here. And then, now at a certain point, we're going to fill up one of these little 12.8 kilobyte buffers. And then what we do is we just add it to the end of one of these linked list chains. Now at a certain point, we have a limited amount of, if we were in an ideal world, we'd just take all of our data, put it in these chains, and then write them all out. But because we have a limited amount of memory, at some point we're going to run out of space to put these linked lists. And so what we do is we have another process where we identify the longest chain that we can find, and we send it off to be written. So we're constantly looking for these really long chains to write out to the data. And what that means is that the longer the chain you can find, the bigger the writes you're doing. And the bigger the writes, the more you can amortize the seek time of the disk arm over those writes. And so the amount of memory you have in your system is a variable that goes into how long these chains can be, which goes into how long you can, how efficient you can make your disks. We wanted to kind of look at that relationship a little bit more carefully, and so we built, yeah?
Can you talk a little about data copying? I've lost track of how many memory copies you're actually doing.
That's a great question. So, yes, so we do a lot of memory-to-memory copying, and
we were that bandwidth problem.
Yeah, so the question was, isn't memory bandwidth a problem? We thought it really would be. So we ended up rewriting our system 3 times, and the first time we were very concerned about memory copying, and then we found out that for us, we do not run into memory bandwidth problems. So we either had network problems or we had I/O problems from the disks. And so it is important to realize that the disks that we have can only support about 6.4 gigabits a second. And so in our particular case, that ends up not being a problem.
And is all this being done through syscalls? Is that an overhead problem or not?
Yeah, so the question was, is this being done through syscalls? Is that a problem? Yes, so all of the memory copies we're doing are done with like memcopy, for example. Syscalls didn't end up being an issue except for in the network layer where we were doing very small writes. And so originally that was kind of a problem. But we end up writing out, I want to say, the send calls that we do, we are able to issue enough send calls. We do not exceed the number of syscalls that we can handle. Yeah, so that's not a problem. Yeah. We're kind of actually investigating, this isn't on the slides, but we're looking at replacing some of that network code with a user level network implementation. And so we're going to kind of see what that does. But yeah, we keep fighting the biggest bottleneck that we have, and memory bandwidth was never one of those bottlenecks. We also kind of looked at NUMA effects. We were like, our system has 24 gigabytes of memory, but it's divided into two 12 gigabyte banks in 2 NUMA domains. So half our cores belong to one domain, half the other. And we thought maybe that will be an issue. We did some experiments again, ended up in micro benchmarks being about 15% throughput overhead, but in actual application performance, it didn't really show up. So we looked at this case. OK, so now we have this trade-off between chain size and disk speed. And so what we did was we did a micro benchmark where, OK, so this graph on the top, what you're seeing is actually the mean throughput as a function of the number of files that we're writing to. So the number of logical disks per physical disk. And it goes up to 300 something, which is what we ran in our system. And no surprise, the bigger the write you do, the more bandwidth you get. So you've got something like 82 megabytes a second if you're writing 80 megabyte chunks. But if you're writing 5 megabyte chunks, it goes down into the 60s or so. So you lose about 15, 20 megabytes a second by using smaller writes. But the kind of interesting thing is more about what happens on the bottom. This is the variance of the throughput as a function of these writes. And what you can see here is that as you get a lot of files and as you're doing a lot of seeking, the smaller the writes end up introducing a lot of variance into the performance you get from the disk, which is not surprising because sometimes you write data that's close by, sometimes you write data that's kind of farther away. And so another thing that definitely affects the performance of the system as a whole is not just the average throughput, but it's very much the kind of variance you see as well. And so given the physical resources that we had in our system, we could support about 10, 12, 20 megabytes chain sizes. So just to remind you, at this point, now we've got all the data that belongs where it belongs in the right files, and that makes phase 2 extremely simple. So in this particular case, what we have are some input disks that we read data off of. We just pass them to an in-memory sort, which happens to be radix sort, and then we just write it back out again. And we picked logical disks. So we have 8 cores, and we picked our logical disk sizes such that all of our cores can be sorting in parallel. So we can't quite make 24 gigabyte logical disks, even though we have 24 gigabytes of memory, because effectively we need to divide that by 8 because we have 8 cores. But then we also divide that by 3 because of the fact that we want to triple buffer these things. So we want to be able to read data into one buffer while we're sorting data and while we're writing it. And so there's multiple buffers per sorter in this case. And so this is the kind of architecture that basically resulted from implementing the system. And I want to just talk a little bit briefly about some of the results of our manual tuning. So that system maybe took about a month or something to build. And we had a couple alternative designs. One that was based on a merge sort implementation, which is what Hadoop uses internally if you know about its shuffle phase. What we found in that case was that if we tried to merge sort over a large number of files, 2,500 files, you end up becoming extremely seek limited. Because a disk can only handle maybe about 60 seeks per second, because it's got about a 15 millisecond seek time, plus rotational delay. And so the second that you need more than 60 seeks per second, that becomes kind of a bottleneck. And so the way, a kind of well-known way of handling this problem is to merge sort in batches. So you can merge sort a subset of files and then kind of build a pyramid of sorting up the top that's sort of log height. But then the problem with that is that we had this kind of goal that we wanted, which was that we wanted to always mutate data every time we did an I/O operation. And so if we did a batched merge sort implementation, we would have a situation where we're basically reading and writing data multiple times, and we kind of wanted to avoid that. Yeah?
It's a really naive question. There's obviously a bunch of caching on the disk these days. Does that get in the way of your intuition of how the device is going to behave?
Yes, that's a great question. So There is a lot of caching in the disk. We learned we learned all these the lessons that aren't in here about like operating systems and how complicated they are. But the disks themselves have 32 megabytes of cache on them, and they use this thing called NCQ, network command queuing, I think, which stands for which basically means that you can have multiple requests on the disk, and you can reorder them to be more efficient. So that's one set of optimizations that live in the disk itself. We have these RAID controllers that have 8 disks per controller, and that has 512 megabytes of memory as well. So there's 512 megs of memory that is shared among those 8 disks. And then, of course, we have all this DRAM, and the operating system is trying to do this operating system level buffer cache. And so there's a lot of extra copying going on there. Now, in our case, we have a kind of unusual workload in that we're reading all this data out and then we're writing it out. And so we don't have locality in terms of memory. So we wanted to disable that buffer cache entirely. So there's this feature called direct IO, which basically is a programmer directive that can say, I know I'm not going to need this, just go ahead and don't even put this in the buffer cache. And so we enabled that, and that helped a lot. What we really want are, in a sense, to be able to treat each of these physical devices as a linear system. So it would be great if we could say, what's the speed of the disk? It's 80 megabytes a second. Now it's 70. If I do this, it'll go back up to 80. But what ends up happening is if you end up issuing data sort of slower, if you end up issuing data at a lower rate than the disks can handle, then what happens is they're able to drain this cache out to the disk. So you're always hitting the cache. And so then you get this really weird numbers. So like we have all these tools that will show us like what is the speed of our writer, and it's like 700 megabytes a second, even though we know that the disk can only do 100 megabytes a second, and it's just noise from this cache issue. And so in order to characterize the disk for some of the work we're doing now, we had to build some micro-benchmark programs that would basically make sure that we filled up that cache. So these are all the different stages. We've got phase 1 in the top, we've got phase 2 in the bottom. And these are each of the stages that we implemented. We have the number of each of these stages. So we have, like, for example, 8 readers and 3 node distributors, et cetera. And then we have a sense of what the total throughput is in megabytes per second that each one can perform. And then the thing to pull out of this that's kind of nice is that in both phases, the writer is the bottleneck, which is something that we wanted going into the system, because in general, you can read from disks very slightly faster than you can write to them. And so in our system, we knew a lot about how the disk performed. And so we could read it about 100 megabytes a second on the outer tracks, but we could only write it maybe 85 megabytes a second or something like that. And so we wanted a system where the writers were constantly busy, because that was our bottleneck. And in this case, they are. So then we computed what % over that bottleneck stage are the rest of the things. And remember, if things were ideal, this would all be 0% on the right column. And so in terms of our input disks, we're about 13% over sort of our node distributor. Because we went from 2 to 3, we ended up being about 50% over, et cetera. And the thing that will jump out, obviously, is this coalescer stage, which is 30,000% over where it should have been. And that was basically just a mistake. I mean, we implemented, we had these config files that we were running, and all the coalescer is doing is basically taking that linked list of lots of little buffers, and it's copying it to one contiguous buffer so we can send it to the disk. And that's a very cheap operation. And so we ended up accidentally implementing 8. But even if we implemented 1, we'd still be thousands over, because that stage is just a cheap stage. But I guess what's relevant is the fact that at least on the borders between our system and physical hardware, we're actually pretty close, either 0%, and well, something has to be 0%, or 3% or 13%. So we're pretty close from where we want it to be in terms of that. In terms of how balanced we are, in terms of resources, you can see in phase 1 and phase 2 where we are. The thing that what we really wanted to care about is in a sense what the disk was like in phase 1, because that was really the most complicated thing, that we're trying to stage all this data in memory before we got it to disk. And what's nice is that we were able to get about 82% of the sequential speed of the disk, even though we have a random workload. And that was just by trying to write these data chains out in long chains. And obviously you'll see here that 0% network in phase 2 because we don't use it. In terms of CPU, some of our cores are completely pegged. So like our sorter is CPU bound, for example. But again, we used the cores that we had really for process isolation, not necessarily because we needed the compute for them. In terms of scalability, so we had 52 nodes, and we implemented it across them. So the green line is phase 2 that doesn't use the network, so it's trivially scalable. But I guess this sort of purple line is phase 1 that does use the network, and it's pretty scalable up to the point of the support that we had in our switch. And to be fair, we had a lot of bisection bandwidth, so we have a star topology, so that's not an issue. If we were to use kind of a data center network that had oversubscription, we'd be fine up to the point where we got to 6.4 gigabits a second, because that's what we needed. So there's this sorting challenge, that Jim Gray created, and then after his tragic loss, there was a group of volunteers from HP and Ordinal and Microsoft that have continued the challenge since then. And so every year they have this thing. So we took the results from our system and we sent them off, and then we managed to get these 5 records. 2 in the Gray sort challenge, which is sorting 100 terabytes of data. 1 in something called minute sort, which is basically how fast can you do an in-memory sort, memory-to-memory sort in 1 minute. And then kind of, most interestingly, I think, was this sort we did that's called JouleSort, which is looking at the energy efficiency of the sort system. And I just want to say, I mentioned at the beginning of the talk that Yahoo had 3,500 nodes, and then we kind of had this back of the envelope calculation that we could beat them with 30, and it turns out that we ended up using 47. So we're pretty close to where we thought we would do at the beginning. In terms of this JouleSort benchmark, what we did was our servers have the ability to extract from them real-time power draw measurements, and so we kind of pulled that data out, and we ended up computing how long it took and how much power, we used, and we were able to figure out the number of records per joule that we were able to sort in. And what's kind of cool about this result is, and I was talking to Dave Anderson, if you're familiar with the Fawn work, there's this Fawn work that's from Intel CMU, and the idea behind that is to use very, very power efficient components to build large-scale systems. And so they built a system with Atom processors and SSDs, and each of these nodes uses a very small amount of power. And so they're able to get extremely high energy efficiency out of these systems, and it's really awesome work. And so a lot of times when you solve a problem, there might be 2 solutions that are on 2 ends of the spectrum. In our case, we were able to get the JouleSort benchmark as well, and we didn't do anything we have these servers that draw 300 watts, and we never even went into the BIOS and played around with the power savings or anything like that. It's just the sheer fact that we were able to sort that much data with that high of efficiency, and we had that few nodes, is what gave us the thing. So I think, it's kind of cool that there's 2 different ways, in a sense, to think about energy efficiency. We have this particular hardware instantiation, and so we were looking at basically what would happen if we replaced our disks with faster disks. We did that, and we found out that, in fact, it made our system faster, but more importantly, it moved the bottleneck somewhere else. And so we ended up moving the bottleneck elsewhere, which was kind of a good sign. And I think I'm running a little bit out of time, but we also replaced memory by looking at if we had more memory, what would happen. And as it turns out, we were able to write out data in these longer chains, but because the memory wasn't particularly our bottleneck, the system went faster, but it didn't end up changing what the bottleneck was. So like I said, since then, we've generalized to some other applications. Yeah, I'm sorry, what?
Just a question, actually. So since you looked at other hardware or balances, did you also look at or think about other types of hardware? Like what if you had, let's say, flash into the system in the mix, or something completely different?
Yeah, so the question was, what about something like flash or something that's very different? No, absolutely. That was something we talked quite a bit about. We do have some limited flash devices that we put into some of our servers, but at a pragmatic level, we did not have really enough flash to kind of extract interesting information from that. But our architecture, because it's sort of so throughput oriented, what we found was that actually flash drives are only maybe 2 or 3 times as fast as spinning disks in terms of sustained throughput. Obviously, they have orders of magnitude more, random IOPS support. But at least the devices we had were maybe 250 megabytes a second versus 100 megabytes a second. So, we didn't really look too much at that yet. But there's obviously a lot of interesting research. And a colleague of mine, Steve Swanson, has a whole lab that has been kind of looking at some of the issues with that. What's that? We are Steve. Yes, of course. Everyone's from here, of course. So now we have this MapReduce programming model. I'm not going to go into the details of how we did it, but it was very simple, actually. If you have a large distribution sort system, it's actually pretty trivial to build MapReduce, because all you do is when you read data, you apply the map function to it. And then when we're doing this big in-memory sort on the other end, that's a great time to do the reduce function. But it does change the way we kind of think about the system, because it takes 5 minutes to write a MapReduce program, and then we don't want to spend 7 months tuning our system. So we've spent a lot of time lately sort of supporting skew in different ways. So obviously, data records have skew in terms of how big they are. Those can vary by several orders of magnitude. Data distribution across nodes, can have some skew. And those are actually relatively easy problems to solve, because you can do sampling and some other well-known techniques. The other thing that we've really been thinking about lately, though, really is about the kind of resources used by these user-supplied map and reduce programs. And so we have ongoing work in a couple different areas that is really actually ongoing, so I don't have any graphs. But one of the things we've done is we built kind of a meta, what we call, we have a suite of what we call meta programs, where we take all of the log data that we generate during these runs, and then we have a set of programs that will process that log data and give us some information. So in this case, we have one that will tell us what the bottleneck stage is by monitoring how stages interact with these buffer pools and how often they send data to each other. We can kind of figure out if none of my neighbors were a bottleneck, how fast would I go, and then we can reverse engineer what the bottleneck stage is. We kind of have a program that will choose how many instances of each stage you should have. And the way we do that is we take our directed data flow graph and we end up generating a bunch of inequalities based on some of the log data that we saw, as well as some of the things we know about the hardware. Like we know a disk has 100 megabytes a second, so that becomes one inequality. And we know what our network is and some other things. And then we submit them to this giant solver that will tell us how many stages we should instantiate at each point. And then the big thing we've been thinking about lately that we don't really have an answer to right now is how to, so we have all these typed buffer pools that all the stages talk to. And one of the things we want to figure out is how do we allocate memory across those different buffer pools? How much should you give to the different buffer pools? And also how big should the buffers be? And that's kind of there's a very big design space of memory scheduling policies that we could look at. And so that's kind of one of the things that we've sort of started looking at recently, as well as how do you schedule work in order to prevent starvation. For a CPU, this is actually quite easy because you can have preemptive scheduling. So I can pull the CPU away from you while you're working. And once I give a stage a memory buffer, there's really nowhere to put that data while they need it. And so we have to basically come up with a non-preemptive scheduler for memory that also doesn't end up causing a lot of starvation among our stages. So this is the kind of flavor of the stuff that we've been thinking about lately. So just kind of in conclusion, now that we've got warehouse-sized supercomputers that are distributed across tens to hundreds of thousands of nodes, it's obviously important that we really think about closing this gap between efficiency on the one hand and scalability on the other. And so, at least at UCSD, we've been using this Themis JouleSort platform as kind of a research vehicle to look at how do we balance computing in those kind of environments. And so, we've started with sort, then we moved to Mapreduce, and we're also interested very much in going beyond Mapreduce into some other kinds of problems. And so with that, I'd like to thank you for your time.
So we have time for some questions.
That kind of stupid question.
Yes.
The way you guys, when the TerraSort with Hadoop originally was using a custom partition function, which is doing exactly what you guys do. You have to sort of know where you're going to put every tuple by understanding sort of the range of values you're supposed to do. But that doesn't really work so well for general Mapreduce applications. It's kind of a specific kind of partitioning. So when you made this shift from a sort engine to a Mapreduce engine, did you have to sort of change the way you do that initial hashing after the map phase, or is there something I'm misunderstanding that your thing was much more general than I realized it was? Or?
Yeah. So just your question was about if we go from a sort environment where we know where all the tuples are going to go because we have this hash function, and we move to a Mapreduce where we don't really know what the input data is, like how do we deal with that? Yeah. What we do is we added a phase 0 before this begins, where we do a distributed sampling phase. So we end up we sample the input data in a distributed way at the beginning, and we end up building these empirical histograms of where the keys are. Yeah, so we have this it's kind of complicated thing, but basically it's very simple conceptually. So we have this distributed process. We get these empirical empirical distributions, then we merge them, and so now we have kind of a global view of what's going on, and we actually give that to all the nodes, and they use that to kind of do that. And what I'll say is that we tried two different ones. One was based on a tri-data structure, which minimizes memory lookups, but you can't really control skew that well with that. So then we end up using binary search, has a lot more memory lookups, but you can really narrow down the amount of skew in that. The thing, though, is that doesn't work quite enough because you don't just care about getting the input data to the right intermediate data. You also want to not only sample the data, but also sample the transformed data after applying the map function to it. And so what we actually do is we do both. So we get a set of where the keys are to begin with, but then we also apply the map function to that data, and then that's what we pass around.
Philosophical question. Mapreduce has kind of become the de facto way everybody thinks about doing big problems in these kind of systems nowadays because it's the one that's there. Do you guys have any insight into other ways that might be productive to use these kind of huge systems or structure these kind of problems?
Yeah, it's a great question. That's a great question. So yes, we do. Well, I mean, yes, we think we do. There's two things that I would say. One is some work that I'm actually quite interested in personally, which is looking at digital cinema and motion picture production as a kind of challenge application. So it's impossible to see this graph, but that's okay. One of the things that I did was, there's a lot of companies that build these huge high-resolution cinema kind of systems, like Technicolor is an example, Disney's an example of this, and DreamWorks and stuff. And they end up having these really complicated data flow problems. And so this is something I got out of a presentation that's like some digital cinema thing. And if you kind of think about it, what they deal with is they have huge frames of video that they have to bring in, and they do all this computation on them. So we tend to think, when we think of like motion picture production, we tend to think of like streaming things, real-time things, but there's actually a ton of computing that goes on. So at UCSD, we have the Center for Network Systems, and we have these twice a year kind of research reviews. And we invited someone from Disney to come, and they were talking about some of their data center challenges. And they were like, okay, we have 100 terabytes of data, and we have a 100-stage data flow program that we want to apply to that. And we want to do things like adjust colors, add watermarks, timestamps, all this captioning, And they were like, of these 100 stages of processing, like 70 of them are completely I/O bound. It's not rendering, it's just we're taking in data and transmuting it in some way and sending it out again. And so they were like, we end up kind of writing our own custom software, and this is a big challenge for us. And so one of the things that I'm interested in looking at is how could we use a system like this Themis TritonSort system to basically look at data flow programs that aren't driven by ad-based sort of web-based kind of systems. And so I think this is an example of the kind of problem that you might see. The other kind of problem that's really fascinating to me is, Joe Hellerstein at Berkeley they have a lot of work, and others do as well, but I'm just a little bit more familiar with his work on sort of barrier-free data flow programming. If you think about the way Mapreduce works is you materialize all the data every time, and you also have these really strict barriers. And so it's not necessarily the case that every system you build has to be like that. And so at its heart, TritonSort, like any data flow system, there's no inherent sense of a barrier. We just implemented one. And actually, you can see in the energy graphs exactly where that barrier is, which shows up right here, which is the fact that we have like this phase one, and then everything just kind of stops and waits to the straggler. And then the straggler comes in, and then we just start going again. And it'd be kind of interesting. We're interested in kind of reading some of those papers and some others and kind of looking at that as a second place to look for new work.
So actually, maybe another question was for your system. So one of the advantages that Mapreduce has is that it's really great at doing fault tolerance.
Yes.
And is this something that you guys also are handling in your system?
Yes. Your database students are too nice. I told them to ask me about this because it's like we don't have an answer for that. So you notice I didn't talk about fault tolerance. So the thing is that we have a lot of experience running the system, and what we found was that because we're using like orders of magnitude fewer nodes, we didn't see node failure, rack failure, top rack switch failure type things, but what we saw all the time was errors with the disks. And we actually didn't really see disk failures that often. What we saw were these latent sector errors. And so all of our disks basically all have at least a couple latent sector errors, which is basically when I go to read some data and it gives me an I/O error that's unrecoverable. The disk is fine, most of the data is fine, just a couple sectors aren't right on it. And so we have a couple things that Alex Rasmussen is actually looking into to support fault tolerance. So things like recording the data on two different nodes. If you give up half of your efficiency, you can basically replicate the data twice. And if you give up half your network bandwidth, so there are ways of handling whole node failure. But I think in our case, the thing that I'm at least most interested in is how we deal with this latent sector error problem. And people tend to use things like RAID controllers, and we even have RAID controllers, except they're not very good, and they don't work that well in terms of sustaining I/O throughput. So we have 8 disks, we can support 800 megabytes a second. But if you make that a RAID 0 striped data disk array, maybe it goes at 500 megabytes a second. And so one of the things we're looking at is there was some research done by IBM in like 2005, 2006 timeframe on this thing called intra-parity check codes, which is basically, think about RAID, but instead of doing RAID across multiple disks, you just do RAID within a single disk. And the reason, it sounds crazy, because if you lose a disk, you've lost your redundant data as well. But if you think about, there was a couple papers published by NetApp where they looked at about 1.5 million disks deployed in the field, and they looked at all the different I/O errors they found. And one of the things they found was that if you've got an I/O error and you move, I think it's about 50 megabytes in either direction, once you move beyond that, you no longer really have correlated failures. And so as long as you can store a copy of your data sort of far enough away on the same disk, you can actually get rid of a lot of the correlated failures that happen with these latent sector errors. And so that's kind of one of the things that I actually had a student do, was to take the inter-parity checkcode work from IBM, implement it in the system. And what's nice about the reason that you might want to do this is that if you're doing traditional RAID and you have, let's say, 8 disks, at least one of those disks is going to be lost to parity. So that's like a 1/8 overhead. The second that I'm doing RAID within a single disk, I can tune that all the way to like 1,000 to 1. So I can have 0.1 or 0.01% overhead, or excuse me, 1% overhead or 0.1% overhead. And so that's kind of a direction that we're kind of looking at a little.
No, thank you.
Okay, thank you.